Okay, welcome back to the second keynote of today's workshop. And I am very pleased to see most uh, of the participants have joined us back from the orals and a lot more watching us live on YouTube. So just to remind you, you can always go and watch us on YouTube. There is a little lag, only a few seconds lag from the live stream from Zoom. And for today's second keynote, I'm honored to present Professor Mireille Boutin, who's currently an associate professor at the School of Electrical and Computer Engineering at Purdue, and also at the Department of Mathematics. Her research is in the area of signal processing, machine learning, and, well, generally mathematics, with many contributions in the area of inverse problems, processing of discrete structures, and other fields. Please welcome Mimi Boutin, who is going to talk about the geometry of high-dimensional data.
Thank you very much, Alexei. So I'm going to talk about, as you said, the geometry of high-dimensional data. This talk, I must mention, this work is with the help of my graduate students. So I need to thank Alden Bradford. This is Alden, who is a Purdue graduate student in the Department of Mathematics and contributed to that work. There's also Tarun Raju, who graduated here with a PhD in electrical and computer engineering, is now at Qualcomm. And finally, Sung Chun Han, who also graduated with a PhD in electrical engineering here at Purdue and is now at Google. So that being said, let's move on to the topic of the talk. So in this talk, well, we always hear that deep neural networks are like a black box, right? That it's a black box approach. We don't really know what it does. And there's many reasons why it's difficult to explain what it does. And one of the issues is that the data that it deals with is very, very high dimensional. And obviously we cannot visualize high dimensional data very accurately. And in fact, our intuition of what data does, which is acquired from low dimensions, dimension 1, 2, and 3, does not necessarily carry over to high dimensional spaces. And so it's very difficult to understand what is happening really with these with this high dimensional data as being processed by these deep neural networks and other machine learning tools. And so, so trying to understand the geometry of the high dimensional data in my mind is a fundamental way to try to understand, really what is machine learning doing. So let's move on to the problem that I'm interested in. So we know in machine learning, we exploit structures in data to learn, to build models. And so, one very popular, very common structure that we look for is, I'm going to draw things in the plane just because, that's just easier to visualize. So a lot of time, we'll draw some data, some data points in our space. So let's say if it's R2 and we draw them and then we find, oh, well, look, all these points concentrate in some area. So, right, so we got that little area here, and then we say, based on the samples I have a structure, my data is concentrated over there. And so I've learned something from my data. I've learned some structure from my data. Now, of course, you could look at another class and draw data from that other class. And these data points might lie, well, they might actually congregate in different places. So maybe some of them are here, some of them are here. And then from the samples, you could infer that, oh, well, my data accumulates in two different areas, one here and one there. So if you had these two classes and you're trying to recognize them, then you could take these two pictures and put them together, right? Look at the mixture density here. And, again, you would have the fact that your points from the blue class tend to congregate, tend to accumulate over here, and the red points tend to accumulate either here. I'm not drawing the same exact points, but you get the idea. Or there. And based on this, you could design a classifier that would essentially draw a separation, maybe, well, depending on the type of classifier you use, but maybe something like this, right? That says, oh, everything that's in the middle region, I'm going to call this, you know, the blue class. And if I draw a new point, and if it is in the other two regions, I'm going to call this the red class, right? So you use those samples to find out structures, and based on these structures, you can build, for example, a classifier, or you can build other models. So that's the idea that's one example of how we use structures to find to develop a model and to learn. Now, obviously, we have to be very careful when we do this, because we need to have enough samples to be able to make a statistically significant inference about what kind of structure we have in this problem. And so if I go back to my previous example, and if somehow we had much fewer samples, we might actually have ended up with, say, let's say 3 blue points here and maybe just 2 red points there, right? So if we had only a few samples, then we could infer that, oh, the red points congregate around here and the blue points congregate around there. So when we drew our classifier, we would end up separating maybe over here, right? So when we draw new data points, we might have ended up with a new point that lies, say, down here, which we would classify mistakenly as a blue point. Well, it was more likely to be a red point, which we would have known if we had more data to begin with. So a classifier that doesn't not have enough data to be able to statistically significantly inferring the structures may end up not scaling very well. So the classifier does not generalize well. All right, so that is an issue in high dimension, because in high dimension, the points that when we draw points in high dimension, you know, there's so much space. And even if we draw a large number of points, 2,000, 3,000, 10,000, 15,000, 50,000, it still is very little. And so unfortunately, points do not tend to concentrate in high dimension. And there are mathematical reasons for this. I like to give this example. I like to go through this example because the math is so easy, but it's a fundamental fact that people need to understand when they work in high dimension, is that if you take a unit cube in a d-dimensional space and d is large. So here I have a picture of a unit cube, right? So this side length is 1, this side length is 1, this side length is 1, and so on. Of course, I cannot draw in dimension d, but just imagine that there's d dimensions there. Then the volume of that cube, right, is 1 to the d, so that's 1. So it's a unit cube. And if I go ahead and remove a little shell, let's say of thickness epsilon on each side, on like all around the cube. So I will take each dimension, I'll remove a little epsilon here, and I'll remove a little epsilon there, so that now if I look at the inside cube, it has side length 1 minus 2 epsilon in this direction. And I'll do the same for every single dimension. So I'll remove a little epsilon here, a little epsilon there. So this side length is 1 minus 2 epsilon, sorry. And on this one as well, I just removed the shell all around my cube, so that all the side length now becomes 1 minus 2 epsilon. Right. So then the volume of the inside of the cube becomes 1 minus 2 epsilon to the power d, which of course, as d increases, decreases and decreases, and eventually converges to 0 as d goes to infinity. So this means that in an infinite dimensional space, there is a 0 probability of drawing samples inside the cube, so long as we draw from a non-degenerate probability distribution function, of course. But you know, it's not. We don't expect to have points accumulating inside any area, because if you put that area inside a cube, there's a 0 probability of drawing samples from the inside of the cube. In fact, most of the volume is on the shell of the cube. So, and this is not surprising, because we know that a unit cube in an infinite dimensional space is not compact. So we can find an infinite sequence of points inside the cube that has no subsequence that converges. So there's no accumulation point in that sequence. So essentially too much space, right? So what happens because of that is that the data set is going to become more and more sparse as the dimension of your space d goes to infinity. So, and this has been observed in the 1980s, experimentally very often when people were building databases and trying to index these databases for fast search using index structures, using clustering. So, if you take a point in a high dimensional space and you have a training set and you ask what is the closest point to your query, right? And then you compare the distance to the closest points to the distance from the query to the furthest point. And usually you have a different distance. The closest one is much closer than the furthest one. But as the dimension increases, the distance to the closest point ends up being fairly similar to the distance to the furthest point because everything is far away. And this is not a consequence of me picking Euclidean geometry. This will happen regardless of the distance function you put on your space, regardless of the metric you decide to use. It's just a property of metric spaces. And so we have to be a little bit careful that what we imagine happens in low dimensional space does not necessarily happen in high dimensional spaces because things are a lot more sparse there. Now, how big is D to become a problem? Again, from the literature, when people were studying database indexing, the observation was, starting from dimension 23, 20, maybe even 18, things were starting to be problematic. And that if you try to index a database for fast search, when the points that you were indexing were about dimension 20, the search, the speed of the search algorithm you would end up getting with an index structure would be comparable to a linear search, just a sequencer search. So you did not gain any advantage to indexing your database. So it's a well-known phenomenon and it's problematic in high dimension. So how is this addressed normally? Well, this is addressed by going from a high dimensional space to a lower dimensional space, usually by projection. So you take your high dimensional data and you project it to a lower dimension so that you have less space and more points to fill up your space. So just a natural way to do that. Of course, we recognize that when we do this, there may have been some structure in the high dimensional data that were destroyed. We're very familiar with that. Draw an example here. If your points, of course in R2, because that's all I have on my screen, but if your points were separated into like this, right, and you end up projecting in this direction, then you're going to collapse the whole set of points down into your line. And so that separation you had here, right, there was a separation in my initial point, has disappeared. So that structure has disappeared when I project down those points to a lower dimensional space. Right? So we all realize that projecting may destroy structure, but what we also need to remember is that structures may be created as well. The projection process can create structures. We often forget that. And I think we need to remember that a little bit more often because what we create depends on how we project. So if different people decide to project differently, they may create different structures and use these structures to make inferences or to build their models, and they may end up with different conclusions. So the structure we create depends directly on how we decide to project. And this will become very obvious in the rest of this talk. So I want to start with an experiment, something you can try at home, because some of the things I'm going to say are going to be very surprising in this talk. They may be shocking. And so I want to back this up a little bit with something you can try at home and convince yourself that what I'm saying is true. So this is an experiment that I did myself. You can do it yourself. And it uses some high dimensional data. I like to take high dimensional data that everybody has access to. So take, what's a good source of high dimensional data? Well, you all have vacation pictures. Everybody has pictures nowadays. We have tons of pictures. So that's a good source of big data. And so why don't you take one of the high resolution pictures you have from your vacation and use that for this experiment, any picture you want. And so take the picture and let's see, you're going to take the picture, and I'm going to draw the picture here, right? And then you will look at all 7x7 windows in the picture. It doesn't need to be 7x7, but that's what I did just because I need a number. You could take 5x5 and 9x9. So for each 7x7 window in the picture, you end up with that little window, that little 7x7 window contains a lot of data. You can think of it as a point P in a space of dimension 3 times 49. 3 because there's R, G, and B values for each pixel, and you have 49 pixels. So you have a total of 147 dimensions. So P is in R 147. And you do this for every little window inside the picture. So, okay, once you have your point representing your window, this is going to be the representation of that window in a high dimensional space. We're going to do the following. We're going to pick a random vector in our space. So just pick it, don't just pick like 1, 0, 0, 1, 1, 1. No. Pick it really at random. So for example, use a pseudo-random number generator to generate each of the coordinates independently at random following, say, a standard normal distribution. And so that you end up with a very, very random vector. So, and then take this vector and use and project the point you had P onto that vector. So you're going to take P, you're going to take the dot product with your randomly generated vector, effectively looking at the line generated, the line span by the random vector that you just generated, and projecting the high dimensional point down to that line. So you take P dot V, and that gives you a point in R, right? And you do this for every single window inside your picture. So you have P1, you project it, you're going to have another window. For every single window that you can find inside that picture, repeat the projection process, right? So what is happening? Well, we have a set of points in a high dimensional space. We are generating a line at random in the space. Oopsie, that doesn't work. And then we are projecting every single one of those points on that line. What do we expect will happen? Do we expect to be able to find any structure inside the projected points? Right. What do we expect will happen with that? I took high dimensional data, it's real data, it's not synthetically generated data. I picked a random line and I projected all of this data to a line. So I got a one-dimensional set of one-dimensional data points. What kind of structure do I expect to find? Anybody has any idea? Nothing, obviously. We don't expect to find nothing, right? Because, well, there's many reasons, but you just think about it. Why would you get anything in a one-dimensional projection? Why it's going to kill off any kind of structure we have. It's going to destroy it. Or, we know projections destroy things, so we expect it to be destroyed, whatever structure was there. And there's mathematical reasons also to back up this opinion. In particular, a very well-known theorem by Diaconis and Friedman says that under some suitable condition, I don't need to go into the details, but they're fairly straightforward. They're fairly, something that's not difficult to satisfy with real data. Most low dimensional projections of your high dimensional data are going to be nearly the same, and they're going to be approximately Gaussian, so just one blob. Right? So we don't expect anything interesting to happen there, both for mathematical reasons and for just common sense reasons. So you're with me so far? We don't expect anything to happen. So why would you do this experiment? Well, because something surprising is going to happen. So this is an example of picture this is my hand back in the days where we're doing research on sort of the opposite of deep neural network, where we're trying to do a low-cost computation to do image processing on a cell phone to try and read signs and translate them, and all of this on these super old and tiny laptop. Yes, I see the comment. Yeah, we were reading Urdu with a tablet. In those days, the cameras are very crappy, right? So the challenge was, how do you do this with very low computation? Can you find algorithms for recognizing this that are very effective? So this is on the Purdue campus where we put fake signs. Yep. So, and you can see the Purdue campus behind me in case you've never been here. It's a beautiful campus. You're seeing the engineering fountain. That's not a fake background. This is my true background. So yes, boiler up. Actually, I have to say it the correct way, right? Yes. So this is a picture that was taken a while back, but it's just one that I had, and that I kind of like. And so I did it. And this one I actually did myself. I didn't ask my students to do it. I just wanted to show like what would happen if you just try it at home. And so here's what happened with here's what happened with the first projection. Okay, ready? This is a histogram of the projected points. So I started with points, or 7x7 windows represented as before. I took one random vector and I projected all those points on that random vector, and this is what I got. It's approximately what you expect, right? One blob, nothing, no structure, right? Do you see any structure? Well, yeah, not really. There's nothing really significant in there. But here is the second one. It's got something very interesting, namely a dip right here, right? I did not expect to get that, did you? Nobody expect to get that, right? In fact, you can think of this as two clusters. And I am not lying here. This is the second projection that I got by drawing a different random value. So this was the first one. I drew one first random vector, and then the second one I drew another random vector. So the second one I got, yeah, I will. Okay, I see some guys. I'll try to address that as I'm talking. So that's the second one I got. It's completely random. Right now, if I had just said, oh, let's just take 1, 0, 0, 0, 1, 0, 0, probably would not have gotten this. It has to be random. And then you have to be lucky a little bit, right? I was very lucky. So let me show you the 4 projections I did. And I did not want to cheat. I really wanted to do like, why is this so big? A small number of projections, right? So that, I don't want to be picking just the ones that actually have what I'm looking for, right? So these are the 4 projections that I did. So I took 4 random vectors. And so the first one here, this is the second one, and we just have, this is the third one, and you will notice that the third one also has a dip right here. And you could also say that there's 2 clusters in this data. There's like one cluster here and then another cluster there with more members. And this is the fourth one, which is totally boring. It has no structure, right? I hope that at this point you are really skeptical that your reaction is like, wait a second, what just happened? Because that's not something that we would expect, right? I mean, it's too easy, right? In a way, it's too easy. So what do we learn from that experiment? Well, if the experiment is true, and again, I'm telling you to go home and try it if you don't believe that something like this is possible. But when an experiment like this teaches us is that, at least sometimes it may not be that difficult to find structures like clusters in high-dimensional data, right? Because all I did was pick a random projection, project everything, boom, I got a cluster 2 out of 4 times. So maybe things are not as hard as we think they are. But also, and this is also very important, since my projection was random, right? And I did random trials and I got things more than once, probably there's more than one way to find structures in the data. So if you're thinking of clustering, there's probably more than one way to cluster the data. So if you can cluster according to this one random vector, and you can cluster according to this other random vector, well, there may be another one. They're all different ways to cluster the data, right? And so maybe when we do a projection, with whatever method you want, it doesn't need to be exactly this, but essentially all methods that do high dimensional clustering actually do some kind of projection down to lower dimension at some level. And so what choice they make may end up picking one nice way to cluster data, but it may not be the only one, right? I like to illustrate that with my fruit bowl. You can cluster fruit based on colors, like I show there. You put the yellow ones together, the orange ones together, the red ones together, the green ones together, and then you get a very nice and meaningful clustering. I don't think anybody would argue it's not a good clustering. It is a good clustering. But just as well, you could say, I'm going to cluster my fruits according to shape, and I'll take the round ones and put them together, and the long ones and put them together, and then you get a different clustering. So depending on what feature you decide to focus on, you get a different grouping of the data, right? And it's not clear which one's better. In fact, there is no better one. So, I like to think of the problem of clustering as not well posed, and that even if you have a mathematical definition of what closeness is, there's different ways to cluster the data depending on how you decide to project, and each of these ways is equally correct. And so it's kind of a shift of paradigm here a little bit. So, okay, we found that at least sometimes, on one picture, one example, it wasn't that difficult to find clusters. And if you just randomly project the data, you found some cluster. And so it'd be interesting to study that phenomenon for other high-dimensional data sets, the test data sets we have for deep neural algorithms, the data sets we've been playing with, the data sets that represent different things we're interested in, especially the geometric data sets, things that represent things we can see, right? And if we want to understand what kind of structure they form in the high-dimensional space, one question we could ask is, well, is this a data set that is easy to cluster by random projection, just like the one I had before, the one that's generated from my picture? And so while we're seeking to try to understand the geometry of the data, it sounds like one interesting feature to look at, something that's going to tell us something at least sometimes, is how likely am I to find a cluster if I project my data on a random line through the origin? So how can we measure that? So, I mean, there's different ways to measure it. I'm going to describe one, but what I want to explore is what kind of data sets. Are there many data sets that have that property that I just observed? And can I quantify this in a slightly better way? And compare different data sets in terms of how likely they are to cluster. And so let's look at some experiments. So this is work with Tarun and Sangchun. First thing we're going to do is we need some kind of a measure of clusterability in 1D. So remember, I projected everything down to 1D and I got 2 bumps, right? So I need to be able to measure, do I have 2 bumps or do I have 1 bump? And so I've played with this for many, many years, and I found that I've never seen more than 2 clusters after projection. I've never seen 3 or 4 or 5. I've always seen 2. And so because of that, we're going to focus on binary clustering, and we're going to take a statistical point of view. So what we're trying to do is determine if the samples that we have after projection down to 1D come from, 1 blob or 2 blobs, and if their PDF is unimodal or bimodal. Right, so that's the question we'd like to answer with a number. But of course, we don't have the PDFs. We have sample points, which are in R. These represent the projected points. And we assume these are samples of a random variable X with a certain PDF. And we want to measure the extent to which the PDF of that random variable rho of X is bimodal using the samples. And so we're going to introduce a little measure. There's different things we could use here, entropy and stuff. This measure is very simple to compute, so we like to use it. I'm not saying it's the best, but it's a good one. We will use this variable S to represent this quantity. And what does S represent? So I'm going to make a little picture here to illustrate. So essentially, if you have a PDF and you want to know, if you want to measure S, is you try different thresholds T, and then you think of everything that comes before T as your first cluster and everything that comes after T as your second cluster. So the first cluster, the one that's before the threshold, has a certain mean mu1, and the second cluster has a certain mean mu2, and then you measure the variance of the first group, and you measure the variance of the second group. This term right here, I should use a different color. This here is sigma 1 squared, so the variance of the first group. The second term here measures sigma 2 squared, so the variance of the second group, and we divide by the variance of the whole overall distribution just for scale invariance, right? So it's a very intuitive measure that's going to tell us to some extent whether we have 2 clusters or not. So I'm reproducing it on here on top of this slide. Okay, I'm looking at the time here. We're good. All right, so what does that measure? Well, it's always bigger than 0, right? So when it's small, I should have 2 well-separated clusters because I will have a small variance here and a small variance there compared to the overall variance. So small value of S means nice clusters in 2D. S equals 0 can actually be achieved if I have 2 direct deltas. And S large is when I don't have 2 well-separated clusters. So it's a measure that indicates to me if I have 2 clusters. So why do I use this measure? Well, if I go back to my high dimensional data, right, I have my points in my high dimensional space, and I assume these are observations of some random variable P in the high dimensional space. Then I pick my vector V at random, and I project every single P in my high dimensional space onto the line spanned by my random vector V to get a point in X. And I'm going to measure the clusterability of X in 1D by computing S. So picture, high dimensional data. Oh boy, these look like X. I should not do that. I'm just gonna do points. Point, 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 point. This is my high dimensional data. I draw a random line. I project everything to my line, my random line, and this here, these points here can be used to estimate the probability density function of those samples, that the probability density function from which these samples are drawn, and I can measure S. All right. So if my S is large, I say I don't have any clusters. If my S is small, I say I have clusters. Okay, so we're getting somewhere. So the thing is, because my projection is random, S is a random variable as well, right? S is going to change depending on how I project it. So I can take my data set and draw a lot of random projection, and then estimate the probability density function of S. So on the left-hand side, I have an illustration of a histogram, which helps me to estimate the PDF of S. In the same way, I could also look at the cumulative distribution function of S. But regardless, these graphs are going to help me to understand what kind of structure I have in my high dimensional data. All right, so I'm going to skip the next slide. Let's look at some data. Okay. So in this talk, I will focus really on visual data and especially digit data because they have nice shapes. And I think that's one of the main concerns of the folks we have here. And that's something that I'm very interested in my research, those shapes that we have when we represent digits, 1, 2, 3. For this experiment, I use the MFEAT data set, the multiple feature data set, which is representing a set of handwritten digits using 6 different representations. There's Fourier coefficients, there's correlation coefficients, there's pixel averages or Nikkei moments, morphological features. So I have 6 different sets to look at the same exact digits. And so this data set consists of 2,000 points in a 216 dimensional space, so fairly high. So if I want to study the structure of that data set, one thing I can do is compute or approximate the probability density function of S, this measure of separation. And I want to see, am I getting small values of S, large values of S, medium values of S? How's that looking? How does that compare to a distribution that does not have any clusters, like say a Gaussian? So the graph of interest in that picture is really the middle one here. So this is a graph that has 2 lines, and I will highlight one line here. So the line that's right here, I don't know if you can see my blue, yeah. This curve right here represents the probability density function of S. And for comparison, we also drew in a dotted line, which I will draw in red, what you would obtain if the data that you started from in the high dimensional space was Gaussian. And you will notice something very interesting. Well, first of all, those curves have nothing to do with one another. So we know now the data we have is not Gaussian. It's not, because those curves are different. But interestingly, we see a lot of mass here left of the Gaussian. And remember, the smaller the value of S, the more clustered it is, right? And if you actually look at the projection that are in that region, like the ones that have small values of S down here, you see they're very, very well clustered. So all the projections that end up with a small value down here are very well clustered. And this right picture represents one of them. You can see that the MFEAT data set, and the coordinates I use for this is the correlation coefficient, but I have the other ones I'll show you later. So this is just an example illustrating what happens with the correlation coefficients representation, where you do a random projection of this data set and you find tons and tons and tons of beautiful, very, very nice, very clearly statistically significant clustering, like the one I have on the right of this slide. Yeah, disconnect with kernel. I will leave the kernel discussion later. I'm trying to keep the discussions in, but yes, you can definitely extend to nonlinear projection, and we've done that as well. So, but the point I want to make here is that this data set is very easy to cluster, and that is exemplified by the fact that we did find clustering by random projection. And also, more quantitatively speaking, we have no, it's not the same. It's not the principal component thing. So what we found is that actually, if you compute this area here, you get a fairly large number, and this indicates that there's a fairly large probability that you're going to get a split into two if you do a random projection. So this is data that has a high probability of being split into two by random projection. And just for comparison, you might think, well, maybe the data was like too very far away Gaussian and you're just getting the same clustering all the time. Well, no, because if you actually look at another graph, the left graph here represents the distribution of the pairwise distances between the points. When we draw this graph, we hope to find two bumps. I would like to have two bumps. This is the distance, and this is a histogram of pairwise distances. You like to have the left bump for the inner class when two distances are from the same cluster, and you like to have the higher bump for when the points come from different clusters and you measure the distance, and you like there to be like a dip between the two, so you have the points that are inside the cluster are much closer together than they are distance to the other clusters, right? So here we see that the distribution of the pairwise distances is just unimodal. So there's no clear separation between clusters there. It's really like we expect data in high dimension to be just very sparse and everything is more or less at the same distance. Really, there's no clear separation in the data, yet we're able to cluster it very easily by random projection. Now, is this an accident? Is this because I chose these features? Actually, if you look at the other features, so this is the probability density function of S for all the different features in that data set. So it's the same data set, but viewed through different features. So the feed fac, which I just looked at, right? I'm gonna retrace it in blue so you see where it is. Where is it? It's down here. All right, this is feed fac. If you look at just so for this data set, we don't have the true pixel values. We have pixel average of, very small window, I think 2x3 window. So we do have pixel average. So let's look at those pixel average. I'm going to draw them in yellow. So the pixel averages are, where are they? They're this big bump here. Okay, what is that vertical line here? I'm going to draw it in red. That's actually an important line. This is the middle of, that's where you expect the value of S to be for a Gaussian. So that value is actually large. There's no cluster there. We're looking at values that are smaller than that red line. And so this is S for a Gaussian. So we find that regardless of the feature that we use, including the pixel value, we have quite a bit of mass on the left-hand side of that red line, right? Which indicates that as you keep drawing, there's quite a large probability, more than a half, that you'll get something that's more clustered than the Gaussian, which is very surprising. And regardless of the feature you use, in fact, you always have that property that it clusters with a high probability. And if you look at an extreme case, this is very interesting. The morphological features, all the old folks like me, you remember when we worked with morphological features back in the 90s, these handcrafted features that were like, they work. The morphological features, there's only 6 in the data set, so it's a very low dimension. But if you look at the probability density function of S for these morphological features, you get almost a delta right here. They're super clustered. Regardless of the projection you take, they always cluster. So that's amazing. It's they must really encode something that's important geometric. And so very surprising. Oh boy, I have 45 minutes, correct? That's only 5 minutes. Okay. I need to get to my stretch Q model. So what is happening? So the first question I want to ask is, yeah, I'm going to run out of time. What creates that?
After you, it's just a lunch break, so don't worry too much.
Okay, well, I don't want to prevent people from going to lunch, but trying to, yeah, I'll try my best, okay, to get the points across. And so I would like to understand, my first question when I saw that is I would like to understand what kind of structure might exist in a high dimensional space that would create that phenomenon, right? Because I think of the usual structures we use to model data, Gaussian mixtures and things like that, none of them has that property, like what would work to create such a data set? I mean, a data set that you project at random and you get splits with a high probability. And so we can use inspiration from the Dichonis-Friedman theorem to figure out what would do the trick. So what I'm looking for is a data set that is in a high dimensional space that does not really contain any cluster, no structure necessarily, but is likely to be divided into two when I project it on a random line. So that's a question I've asked a lot of people over the years, and I found some answers using as inspiration the Dichonis-Friedman theorem. And of course, what we need to look at is what are the conditions that are stated in the theorem that guarantee that most projections are nearly the same and approximately Gaussian. So we need to violate these conditions essentially for this to happen. So this was an inspiration for the work. So let me show you a model that I think is a much more realistic model for high dimensional data than what we traditionally use. So to build a model, I'm going to start from a cube. So we call that a stretch cube model. So I'm going to start by building a cube and I'm going to stretch it, right? So what's interesting about a cube in a d-dimensional space is, first of all, it has no clusters, right? All the points are distributed, sparsely from one another. There's no clear division of the data into two. This has no clusters. So no clusters. What else? Well, if you think about it, you could project it, say, along this dimension, right? And then you would get that all the points on this side would project to one point, and all the points on that side would project to the other point. You get a perfect clustering, right? So a projection along this axis yields a nice, perfect clustering. But you could also have chosen to use this other direction and project along this direction, and then you would get, again, a perfect clustering. So all the points that are closer would project to one point, all the points that are on the other side would project to another point. You would have, again, a perfect clustering into two. And it's important to know that the clustering, the grouping you get from the first projection is different from the grouping you get from the second projection, right? And in fact, I can project along any axis, along any edge of my cube, and every time I get a different clustering. And each of them is equally valid. They're equally good. It's just my choice of which direction am I going to project down to. And so this is an interesting data set to consider when we realize how the choice of projection we make influences our results, the structures that we find. The groupings that we find in the data are directly related to what direction or what did I declare was noise, what did I get rid of, and what did I keep. And so, all right, so to put this in perspective, do I have time? Yeah, let me do that. So that's kind of important. So I like to see the points of a cube as the Bernoulli processes, right? They're where, so each value of each entry in a cube coordinate and then the vertices of a cube are either 0, 1, 0, 1, or 0, 0, 1. So we can view a vertex of a cube as a result of a Bernoulli process with, say, probability 1/2. So in each coordinate yi, the coordinate takes either value 0 with probably 0.5 or 1 with probably 0.5. And so then I build a corner of a cube by drawing a sample from the sequence of D independent Bernoulli processes. So what does it mean if I say I'm projecting everything down to the first axis, for example? Well, it means that I'm keeping the first axis, I'm keeping the first Bernoulli process, and I'm discarding the other ones, right? So I'm declaring that my first coordinate is my signal, and the rest is noise, and I discard it. So my choice of what is signal and what is noise is what influences my grouping. What am I going to discard? What am I going to keep? I keep either the color of the fruit or the shape of the fruit. These are two different things, have nothing to do with one another, and each one yields a different structure down at the end. So Okay, so we have a good structure here. It has no clusters. It clusters in different ways depending on how you project, but what it's missing is the high probability of clustering in high dimension. As D increases, the probability of hitting a nice clusters when you project a cube is very small. You're not going to hit one. You got to be very, very lucky. So we found a way to stretch the edges, and I don't have time to go through them, but because I want to say something else, but you just stretch the edge in a geometric fashion. If you stretch them the right way, you will generate a high probability of splitting. And we, I have some graph to show experimentally how you can go from a cube and then stretch it. And as you stretch it, you have a higher and higher probability of finding clustering. So this is a model that we think captures more the essence of what's happening in a high dimensional space. If you think about it in RD, if you build a cube, it's going to have 2 to the D vertices. So you could put one data point per vertex, and you could put a tremendous number of points without forming any cluster, right? And so I'm not saying it's exactly a cube, but the essence of it is like a cube, and you put your points on the vertices of that cube. So what I want to show that experiment. So that's I want to show you what happens when I do this clustering process on the digits, on image of digits, what's happening, because I want to understand, if I draw a 0 or a 1 or a 2 or 3, where is my point in this high dimensional space? I want to get a notion of what is where. And so what I'm going to use to map my space is a cube. I'm going to do a random projection of these digital images until I find a nice clustering. And then if I find a nice clustering, I'll say, oh, for each image, I can now tag them with either a 0 if they're in the first cluster, or a 1 if they're in the second cluster, right? So for each image in the data set, I can get a tag or a signature, or call it what you want. It's a mapping to a vertex on a cube in a D-dimensional space. So, all right, I have results for 3 data sets. I was very excited to see the results. They're very cool. So these are 3 different data sets that show digits. They're slightly different. One of them is grayscale. The other ones are, another one is black and white. So I'm using the MFET data set, the optical handwritten digit data set, both from the UCI repository, and I also have the MNSIT data set. And all of these are handwritten digits with different processing. And I wanted to map them to the cubes. So we use this technique called TARP, thresholding after a random projection. And it's a very, very simple technique where we do a random projection n times. So n equal 10, 20, or 50. And then we see which one gives us a nice separation. And then we pick the best one. So it's called n-TARP, or n is how many projections do you do before you decide which one's the best. Because we're working in 1D, it is very easy to check for the statistical significance of our result. And so if I want to make sure that the structure I found is really there, I just need to keep some data, some new data, and then check the statistical significance of that split using a statistical test. And so I can rule out the ones that are not statistically significant and only keep the ones that are truly there. We ran this projection process 50 times. We picked the best, and to get a coordinate, and then we did that again to get another coordinate. Again, we did that 6 times to get 6 coordinates for each one of our digits. So each digit ended up being represented by 6 numbers, 6 binary numbers, say 0, 0, 0, 1, 1, 0. I have 6, 1, 2, 3, 4, 5, 6, right? So this is a vertex on a cube of dimension 6, right? So each digit now is mapped to a vertex on the cube. And it would be nice to know, to understand our data set, we want to know, where are they on the cube? Are they all spread out evenly? Or do they concentrate on some vertices and not others? What is it? I mean, there's a lot of possibilities. There's 2 to the 6 possibilities of signatures or code or profile. And so 64 possibilities. And so, what's going to happen? Let's look at the results. So this is the MFET data set. These are for all the digits that are in that MFET data set. In decreasing order, I'm listing how many points are in one corner. So this is the most popular corner. It has 211 images. The next one has 172 digits. Right? So the first thing I notice is that you have some corners with a large number of images, like 200 is about 10% of the data set, and you have one empty vertex. You also have vertices with just one image. So this here is a way to visualize the geometry of my data set by mapping it to a cube. And I want to emphasize that the data is not clustered, right? There's no cluster in the data. I have mapped it to clusters, the vertices on the cube, by making a choice of coordinates. But I'm destroying empty space by creating that. So that structure does not exist in the original space. In fact, if I kept adding dimensions, I went to more than 6, then things would split. And so let me show you what happens with the RHID data. Again, the same thing. There's one vertex that has 431 images, and there's 2 of them that have no image whatsoever. There's 4 that have 1 image, and so on. So you have a wide distribution, like of numbers of images per vertex. It's very widely distributed. If I go to my largest data set, the MNIST data set, then all my vertices are populated. Now, granted, they're not populated with the same number of images. So some of them, the least popular one has only 150 images, while the most popular one has over 5,000. So now that I have this distribution, then I can ask, okay, what are the images in that popular corner, right? And what are the images in the not popular corner? What's the difference between them? Do I find all the same label in that popular corner? Is it just all 7s? Or is it mix of labels? How does that work? And so I have a lot of data to look at. I love to steer data. I don't know if you're like me, but this is what happens with the MFeed data if I look at the most popular corner. So this corner has a total of 211 images on it. And this is the coordinate of that corner. And I know I'm trying to wrap up here. But you can see that no, the labels are not the same. It's not just one digit that is mapped to there. In this graph, you see that this corner is populated with a lot of 6s, a good number of 5s and 4, also some 8, and a few 0s and 1s. What does it encode? On the right-hand side, I have the average image of all the images that are in that corner. So what do we see? It sounds like this corner is concerned with, let's maybe try trace in red, like things that have a structure like this and that together, right? If I look at the next corner, again, I have more than one label for it. I have a lot of 2s, some 7s, and some 9s. So what does that corner represent? What's the, it is putting images together that have sort of this thing in common, right? Yeah, this one is interesting because if I go to the next slide, all I'm changing really is this 1 digit. So I take this 1 digit here and I'm changing it for a 0, right? It's another popular corner, and I'm going back here and forth between the 2. You see the average image is very similar, except the top part here is more round than here. So it's like this one has a more square shape. And in this case, you have more 7s than you have 2s in it. All right, I want to show you one that has just 1 label. So this is for the ORHD data. This corner right here, the one that has coordinates only 1, is actually quite populated. It's the second most common vertex, has 334 images on it. And essentially, almost all the images on it are 0s. And you can tell from the average image that they look like 0s. There are a few 9s and 8s, but very, very small number. And so forth. I mean, this very, very interesting data here. MNIST data, here's another example with the code 010011 versus 010010. So only the last digit is different. In the first case, we're getting essentially 1s. And this is what the average image looks like. And in the second case, again, we have essentially 1s, but this time they're straight. right? So that one feature gives us this slant somehow. Not sure how that happens, but it does happen. So we're starting to be able to visualize what happens in a high dimensional data set by mapping these points to a cube. And so they do not lie on a cube to begin with, but I'm mapping them to a cube with my random projection process until I find some good results. So I'm choosing directions of information, things that split very well, and that's how I decide to represent them. Now, if I had time, I could show you what happens if you do this hierarchically, right? And then you do just usual clustering, you know, TARP split into two, TARP split into two, and try to cluster a whole entire data set that way. How does that perform? So we're very curious because that algorithms run very, very fast. And we found that actually in all the data sets that we tried, it's among the best clustering algorithms for higher dimensional data. And it seems like the higher the dimension, the better it performs. So super fast, super trivial. Yet it outperforms algorithms that were very sophisticated to deal with high dimensional data clustering. And so we're very surprised about that. But now that we understand this cube model, it's not that surprising. And so I have to stop. I just want to summarize what we have seen. I guess if there's something you can get from my talk, I hope it's that, you know, this idea of clusters in high dimensional data, this traditional clustering paradigm is not appropriate for high dimensional data. There's no such thing in high dimensional data, but alternatively, we want to think about a sparse data model that has no cluster, but is still likely, maybe sometimes even highly likely to be clusterable by random projection. And like the stretch cube model is one model that is that works. It has these properties. I'm not saying everything follows that model, but that's at least one possibility that seems to be applicable to the data that we encounter. And here's the necessary acknowledgments for the NSF funding and some references. And I apologize for going over time. Thank you very much.
Okay, thank you for this wonderful talk. I think that you have probably solved, you know, you saved me from doing my job as a, you know, Q&A guy and probably have answered most of the questions. However, if we still have some questions, so Bernard, has anyone answered anything, asked anything, sorry, asked anything
No,
on?
I don't see anything on YouTube yet, but I asked YouTube for questions.
Yeah, okay. So we're like maybe 10 minutes post, 10 minutes late. So let me actually ask one question myself, if you don't mind.
Sure.
This methodology that you have described, it sort of provides a nice and mathematically sound way of actually discovering clusters and in some sense assessing this clusterability. However, it would be nice if you could clarify a little bit regarding the computational side of this kind of methods. So is it practical? Is it scalable?
It's super fast. It's super fast, and I did not go into the whole simplification of things, but the quantities we're computing are very, very easy to estimate. So very, very fast. So, you know, it's hard to say that a super simple and super fast method is going to beat up all those sophisticated methods that we've developed to analyze data, and I'm not sure that's the point I want to make there. But I think it gives us a way to visualize. Like I would love if I had. You know, I want to do this. I want to see, like, as you go through process through a neural network, what happens to your data, right? What does it do to it? To, you know, how do we go from data to information and try to, you know, see inside that black box? And I think this is a way to see inside that black box.
Yeah, and there's also a question from Evgeny, who has accidentally asked in a private message. So what about the moon dataset, which is nonlinear actually?
Yeah, so it's not difficult to get nonlinear projection. You just have to extend your coordinate space using like kind of like the kernel trick, or you just take powers of your original features and you find nonlinear separation. What we tend to do is we look for linear ones, and if we find some linear ones, we're happy and we can actually get some information. I've never seen a case where we didn't see any linear ones, but still we did process and find second order, third order ones as well. The memory management becomes a little bit more problematic, but it's still very fast. And so yes, it can find nonlinear separation as well.
Yeah. All right. And the same question from Geraldine as well in the chat. So you're sort of answering ahead of time. Thank you so much. And if we don't have any more questions, then I think we're ready to go for lunch and a little bit of relax. For instance, we have like, it's 10 p.m. in Moscow, and we have a wonderful evening here. So, okay, thank you.
Everyone.
Thank you very much.